Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fragility and Vulnerability Assessment of Monolithic Building Construction Alina Sakir M. Tech Student, Structural, Department of Civil Engineering YCET Kalam, India Abstract. The thesis aims to study the modeling and analysis of monolithic building using ATABS. Modeling of normal framed building and regular monolithic building have to be conducted. And analysis and modeling of different plan irregular building, vertically irregular building which includes setback and step-back structures using equivalent static analysis, modal analysis, response spectrum analysis and fragility analysis. The earthquake response of the building and damage assessment and are found out by comparing the analysis result. Using Hayes' manual damage indices due to the earthquake should be worked out and fragility curves should be generated using percentage of damage on y-axis and peak ground acceleration on x-axis. Keywords ATABS Monolithic Building Construction Fragility Analysis Hayes, Ground Acceleration Introduction Monolithic structure means the whole structure along with the slab is casted at a time. In order to construct a monolithic structure we required formwork for construction. In this project we discuss about the importance of use of monolithic construction work for high-rise building. In accordance with the importance of time, it is feasible method for construction of the repetitive construction work as compared to conventionally applied method of construction. In this work we use aluminum formwork. Monolithic construction work is able to deliver good quality and durable structure in cost-effective manner. It has been used in development of silos, residential building, schools, stadium, and roof of industries, nuclear reactors, pressure vessel, and auditorium. In monolithic structure we used formwork which provides proper alignment, smooth surface and good quality work. Due to use of formwork it increases the speed of construction as compared to conventional method. The progress of any country can be only judged by the progress of the construction industry of the country. Cost and time are the two important entities which plays vital role in any construction activity. Hence it has become necessary to estimate cost and time required to complete the construction. Indian construction industry has started using a number of the arena elegance technology. At same time, progressive rise in stock of construction industry in India and rapid growth of population and urbanization has led to shortage of accommodation and situation has become critical in urban and metropolitan areas. For construction of mass building works, it's far important to have progressive technology that are capable of fast construction and are able to construct best quality and durable construction in cost-intended manner. 1.1 Fragility and Vulnerability Assessment. Recent studies shows that structural performance of reinforced concrete, RC, buildings always play crucial roles in terms of earthquake losses. Structures already built are vulnerable to future earthquakes. Damage to structures cause deaths, injuries, economic losses. Earthquake risk is associated with seismic hazard, vulnerability of building, exposure. Seismic risk measures the likely ground movement that can happen at site. Tools specifically defined for crisis administration and seismic danger moderation arrangements must be defined. Vulnerability assessment reveals the damageability of a structure under varying ground motion intensities. The aim of a vulnerability assessment is to obtain the probability of a given level of damage for a given building type due to scenario earthquake. Vulnerability of structures to ground motion effects is usually expressed in terms of fragility curves or damage functions that take into account the uncertainties in the seismic demand and structure's capacity. Fragility curve is a statistical tool developed for the vulnerability assessment in different field. The outcome of this assessment can be used in loss estimation, which is essential in disaster mitigation emergency preparedness. Two objectives to find out the effectiveness of monolithic building construction technique in various types of buildings. Comparison of monolithic building with normal framed building. Analysis of various types of monolithic building using different analysis method. Comparison of different monolithic building. Regular building plan irregular building vertically irregular building which includes setback and step-back buildings. IJERT 10 is 060217 www.ijert.org 531. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Building Response and Damage Assessment of Different Types of Monolithic Structures Story Drift Story Stiffness Story Shear Wall Axial Load Wall Shear Force 3. Methodology SL number 1 2 3 4 5 6 7 9 10 11 12 13 14 15 16 Component Model Story Height Beam Column Wall Thickness Material Grade of Steel Slab Thickness Seismic Zone Importance Factor Type of soil Type of structure Response Reduction Factor Live Load Floor Finish Values G plus 10 3M 300 mm x 380 mm 450 mm x 450 mm 150 mm M25 FE 415 200 mm 51 Soft Soil Concrete 53 KN/M21 KN/M24 Modeling in the first phase of my project Irregular G plus 10-story framed building and Irregular G plus 10-story monolithic building was considered to study the behavior of both the building and hence compare the results. In the second phase of my project several monolithic buildings were considered which includes plan irregular building vertically irregular building. Figure 1. 3D view of square building asymmetric or plan irregular structures are those in which seismic response is not only translational but also tensional and is a result of stiffness and or mass eccentricity in the structure. From the dynamic point of view a plan irregular building is that for which one or more rotational modes have a significant participating mass ratio. Figure 2. C-shaped building 3D view IJERT 10 is 060217 www.ijert.org 532. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 On comparing the normal framed building with monolithic building construction. On conducting several analysis method it is clear that the monolithic building offers much more rigid or offers less vibration fundamental time period, SEC, 0.195 0.2010 0.176 0.1820 0.177 0.184 0.187 0.178 Figure 3, I-shaped building 3D view Pi 1 Pi 2 Pi 3 Pi 4 Pi 5 Pi 6 Pi 7 Pi 8 Figure 5, comparison of time period of monolithic plan irregular buildings Pi 1 square shaped Pi 2 C-shaped Pi 3 I-shaped Pi 4 L-shaped Pi 5 opening Pi 6 plus shaped Pi 7 step-shaped Pi 8 T-shaped Figure 4, L-shaped building 3D view Different types of plan irregular buildings were modeled which include C-shape, L-shape, plus shape, I-shape, building with opening, step-shape, T-shaped building. V.Analysis A equivalent static analysis The natural period of building is calculated by the empirical expression prescribed in the code. The total design seismic base shear calculation and its distribution along the height are done as per IS 1893, Part I, 2002. The seismic weight is calculated using full dead load plus 25% of live load. B. Modal analysis or mode superposition method is a linear dynamic response procedure which evaluates and superimposes free vibration mode shapes to characterize displacement patterns. Mode shapes describes the configuration into which a structure will naturally displace. See response spectrum analysis for response spectrum analyses. Earthquake ground acceleration in each direction is given as a digitized response spectrum curve of pseudo-spectral acceleration response versus period of the structure. I-shaped building shows highest time period due to longer length of projections and more re-entrant corners. Square shape shows least time period. Figure 6, comparison of base shear of monolithic plan irregular buildings. Base shear is highest for building with opening since mass and stiffness is null at the center. Base shear is least for square plan. This is due to the pattern of mass and stiffness distribution. IJERT 10 is 060217 www.ijert.org 533. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Figure 7, Comparative results of stiffness in X direction. In X direction stiffness is maximum for I-shaped building due to its symmetry. For plan irregular building, stiffness depends on symmetry of the building. Figure 10, comparative results of wall shear on top. Here also plan irregularity is irrespective of wall shear force. Figure 8, comparative results of story drift in X direction. In X direction the drift is maximum for step shape, L shape, and T shape. For plan irregular building, Story drift is maximum at the middle stories. Figure 9, comparative results of shear in x direction. Here plan irregularity is irrespective of story shear. Figure 7, comparative results of axial load on top. Plan irregularity is irrespective of wall axial load. 6 conclusion, monolithic building has less time period, high base shear, more stiffer and heavier than normal framed building, hence vibrates less. Since the amount of drift is constant throughout height, there is less chance for sudden damage in monolithic building. The response of the monolithic building with plan irregularity. Time period is highest for I-shaped building due to length of projections and number of re-entrant corners. Base shear is highest for building with opening due to null mass and stiffness at the center. Story stiffness depends on symmetry of the building. Top stories of the monolithic building has less stiffness and story shear. Story drift is maximum at the middle stories. Plan irregularity is irrespective of story shear, wall axial load, wall shear force. Acknowledgement. The author wished to express her special gratitude to Anjali Sudhakar, Assistant Professor, Yanis College of IJERT. 10 is 060217 www.ijert.org. 534. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org. International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Engineering and Technology Kalam. Above all, the author thanked God Almighty for His grace throughout the work. References: 1 Prasad Kolkar, Vishwajit Nigade, Shivaji Hajare, Prathamesh Campbell, Sagar Patid, Amit Kumavat, 2020, Analysis and Comparison of Mavan Formwork System with Conventional Formwork System. International Research Journal of Engineering and Technology, IJERT, Volume 07 Issue 06 June 2020. www.irjet.net. 2 Ali Kodham Salil, 2018, Design and Analysis 10-Storied Building Using ATAB Software. 2016, International Journal of Research in Advanced Engineering and Technology, ISSN 2455-0876 Volume 4, Issue 23. B. Kranthai and Dr. J.S.R. Prasad, 2018, Seismic Vulnerability Assessment of RC Precast Buildings. International Journal of Civil Engineering and Technology, IJCET, Volume 9, Issue 8, August 2018, pages 217225, Article ID, IJCET_09_08_023. Balin, Michael B., and Cecilia M., 2018, Seismic Vulnerability Assessment of Adamson University Building as Built Using Fragility Curves. Global Journal of Researchers in Engineering Volume 18 Issue 1 Version 1.05 Nikita Patel, Namrata Verma, 2017, A Study in Monolithic Structure, International Journal of Mechanical and Production Engineering, ISSN, 2320-2092, Volume 5, Issue 11, November 2017. 6 Professor R.B. Bajare, Shubham Deshmukh 1, Ashvin Mahajan, Ruhi Karnataka, Indrayani V. Patil, 2017, Page Remedies to the Common Deficiencies Faced in Mavan Technology at Malin Rehabilitation. IOSR Journal of Mechanical and Civil Engineering, IOSR JMCE, 7 Sapna S. Nair, Dr. G. Himalatha. Dr. P. Muthupriya, 2017, Vulnerability Assessment Using Fragility Curves, International Journal of Applied Engineering Research. ISSN 0973-4562 Volume 12, Number 9, 2017, pages 8. Devang Gohel 1, Dr. Jayesh Kumar Pitroda, 2017, A Critical Literature Review on Comparative Study of Conventional Structure with Monolithic Structure. Volume 5, Issue December 4, 2017. ISSN 23202882 IJCRT 17042884 International Journal of Creative Research Thoughts. IJCRITE, www.ijcrt.org. 2229 Pawan M. Walvakar 1, Hemant L. Sonawaitakar, 2017, Seismic Performance Evaluation of Mavan Structural System v/S Conventional Structural System with Effect of SSI by Pushover Analysis. International Research Journal of Engineering and Technology, IRJET, Volume 04 Issue 06 June-2017 www.irjet.net. 10 Dhanalakshmi P., Ramesh B. M., 2017, Seismic Vulnerability of Plan Irregular RC Building with Soil Structure Interaction, International Research Journal of Engineering and Technology, IJERT, 11 Deepika Ramanathan, 2017, studied the increasing adoption of shuttering to boost Indian formwork market. International Journal of Mechanical and Production Engineering, ISSN, 2320-2092, 12 Meghavesaveda and Dr. V.R. Patel, 2016, Development of Fragility Curves for RC Building using Hayes Method, International Research Journal of Engineering and Technology, IJERT. 13 Summit A. Patel, Professor A. R. Darji, Professor Dr. K. V. Parekh, Professor Bhavik R. Patel. July, 2016, Fragility Analysis of High-Rise Building Structure Volume 3, Issue 7 Journal of Emerging Technologies and Innovative Research, JETIR, www.jetir.org. 127 14 Ronijoy, Dr. C. K. Prasad Varma Tampan, 2016, Development of Analytical Fragility Curve. A Review. International Research Journal of Engineering and Technology, IJERT, Volume 03 Issue 15 Taranum Yasmin, A.J. Chaurasia, S.K. Bhattacharya and Jalaj Parashar, 2015, Fragility Analysis for Seismic Vulnerability Assessment of Buildings, A Review. International Research Journal of Engineering and Technology, IJERT, Volume 02 Issue 06 www.irjet.net. 16 Georgios Chanis and Michael Anfardis, 2014, Seismic Fragility Curves for Reinforced Concrete Buildings and Bridges in Thessaloniki. 17 Demetrius Vamvatsikos, Athanasia K. Kazansi, 2013, Seismic Fragility and Vulnerability Assessment Using Simplified Methods for the Global Earthquake Model. Compton 2013 4th ECOMAS Thematic Conference on Computational Methods in Structural Dynamics and Earthquake Engineering. 18 M. Sadki, M. Hosseini, 2012, Developing Fragility Curves for Seismic Vulnerability Assessment of Tubular Steel Power Transmission Tower Based on Incremental Dynamic Analysis, WCEE. 19 G. M. Calvi, R. Pino, G. Magans, J. J. Bomber, L. F. Restrepo-Vilez, and H. Crowley, 2006, Development of Seismic Vulnerability Assessment Methodologies over the Past 30 Year. ISET Journal of Earthquake Technology, Paper No. 472, Volume 43, No. 3, September 2006, pages 75 to 104. IJERT 10 is 060217 www.ijert.org. 535. This work is licensed under a Creative Commons Attribution 4.0 International License.